Hello students, welcome to Educate. Today we are going to study Newton's law of cooling. So what does Newton's law of cooling state? So statement is given here. We can read it together. So according to Newton's law of cooling, the rate of loss of heat minus dq by dt of the body is directly proportional to the difference of temperature delta T, that is T2 minus T1 of the body and the surrounding. So this law holds if temperature difference is small. So let's see its mathematical portion. So we can say that rate of heat loss. So heat is Q, rate d upon dt of Q, negative sign because it is loss, proportional to temperature difference. So T minus T0. Here we have taken T0 as temperature of surrounding and T is temperature of the body. We need a constant, so minus dq by dt is equal to a constant T minus T0. Also you can take T1, T2, etc. That does not matter. Anyone you can use. Here in place of T0 they have used T1, so it's okay. Now you know dq equal to ms delta T or ms dt you can write. That will be better. ms dt. Here dt is change in temperature. Here dt is change in time. Correct? So we can write in place of dq ms delta T. So minus ms, s is specific heat, and right, dt divided by small dt is equal to, this will become k times T minus T0. Up to here any problem? No? Then take dt to RHS and you can do one thing, T minus T0 to LHS. So you will get dt divided by T minus T0 equal to minus k upon ms times dt. Any problem? Here k is constant, m is constant, specific heat is constant. So we can replace it by another constant. Right? So we can write dt upon T minus T0 equal to say k1 and dt. We can integrate it. If we integrate, if you remember, integration of dx upon x is log x base e. So here this will become dt, sorry, so you are integrating it, so this will become log T minus T0 equal to minus k1 T plus c. Right? Did you understand? So we have got log, this is base e, keep in mind. So log of T minus T0 equal to minus K1 T plus C. There is one rule. If you want to remove log from LHS, then RHS goes to e to the power. Means it becomes power to the exponential. That is, suppose you have log x equal to y and the log has base e, then x will be e power y. So this is rule, right? Same rule we are going to apply here. So this will become T minus T0 equals e to the power minus k1t plus c. No problem? Now, you can write it, power rule, you can apply e power a plus b becomes e power a into e power b, and this So this will become e power minus k1t into e to the power c, and this is another constant. So again you can take third constant. Say let's write it as c. So t minus t0 equal to c times e to the power minus k1t, or t equal to t0 plus c e to the power minus k1t, right? So this is Newton's law of cooling. I think you have understood. Here, if we plot the graph between log t minus t0 and the time, we get the graph like this. Here, graph is shown. This is the graph that is plotted between log t2 minus t1 or t minus t0 and t. So we get a straight line, right? Now we are going to see one numerical based on Newton's law of cooling. A pan filled with hot food cools from 94 degrees centigrade to 86 degrees centigrade in 2 minutes. When the room temperature is at 20 degrees centigrade, how long will it take to cool from 71 to 69 degrees centigrade? Right. So here we can apply practical form of Newton's law of cooling that says change in temperature divided by time equal to constant times delta T, right? So here what is happening in our question? In our question, the average temperature of 94 degree and 86 degrees is 90. First of all, we have to find out the average temperature. 94 plus 86 divided by 2, that will be 90 degree. And here, which is 70 degree above the room temperature, right? Room temperature is 20 degree. So now under these conditions, the pan cools 8 degrees centigrade in 2 minutes. In our question, it is given that in 2 minutes, here 94 degrees centigrade to 86 degrees centigrade. So temperature difference will be 8 and time is 2, and k times temperature changes. So temperature change, you have understood that it is just how much? Here is 20 degrees centigrade, right? So 20, when you subtract from 90, the average temperature, right? So you will get 70. So this 8 degrees centigrade divided by 2 minutes equal to k times 70. Now second time, there is another condition. The average, again, here we are talking about 71 degrees centigrade to 69 degrees centigrade. So again you have to find out the average temperature. So average temperature of these two is 70 degree, which is 50 degree above the room temperature, right? From here it is 50 degree. So in RHS you will write this, right? So 2 degree difference, 71 to 69. So 2 divided by time equal to k times 50. And now you have one equation, this is another equation. If you divide the two, you will get t equal to, here time is to be found. Earlier it was given 2 minutes. Here time is to be found. So 2 degrees centigrade, 8 degrees centigrade divided by 2 minutes, and 2 degrees centigrade divided by time, that is to be found. And k, here one is k into 70, another is k into 50. And you will get time 42 seconds or 0.7 minutes. I think you have understood. If you wish, we can analyze what is happening. 94 to 86, right? And time is 2 minutes. And then 71 to 69, and time is to be found. So here first of all we take average. Average time will be 94 plus 86 divided by 2. That will be 90 degree. And then we compare it from this temperature, room 20. So difference is 70. So when we write formula, here we will write 70. Right? So change in temperature, that is just 8 degree, 94 to 86 divided by time taken is 2 minutes and equal to k times. And here room temperature is 20 and its average temperature is 90. So we write that value here. So we get first equation. Similarly for second one, it is 71, 69. Its average we find. So that will be 70 and that is just 50 degree above this value because room temperature is 20. So here we write 50 and the temperature difference is 2. We have to find out time and hence we can evaluate. I think you have understood. Now, there are some more concepts like Wien's law of displacement and one or two more formula. So I'm going to tell you and then I will tell you the practical form of Newton's law of cooling. But let's take one more example. Question is, a body cools from 60 degrees centigrade to 40 degrees centigrade in 7 minutes. Right. What will be its temperature after next 7 minutes? What will be its temperature in next 7 minutes? Right. So let's solve it. T1 is 60 degree, T2 is 40 degree, and room temperature is given as, here I left, room temperature is equal to 10 degrees centigrade. So let's write it as T0 is 10 and time is given as 7 minutes. So we can write the formula MC, this practical form, T1 minus T2 divided by time taken is K times average temperature, that is T1 plus T2 divided by 2 minus room temperature. So this is practical form of Newton's law of cooling. Here we have to put the values. So in first case, MC T1. T1 is how much? It is 60 to 40, right? So difference 60 minus 40 divided by time is given as 7 minutes. If you want to convert it into seconds, so you can multiply by 60 equal to K times. What is average temperature? So average is 50. So just write 50 minus what is room temperature? It is 10. Right? We can denote it as equation number 1. And then in next 7 minutes, so we will start from here 40 and next temperature we will get. So let's write this. So MC 40 minus, say, temperature is say we are getting something new, say here we denote it as T3 divided by time is same, 7 into 60 because next 7 minutes. K times average temperature. If you are taking T3 and in the beginning it is 40, so T3 plus 40 divided by 2 minus room temperature, that is 10. Now this is equation number 2. You have MC this much times this much, and here you have MC times this much equal to this much. If you divide the two equations, so easily you can get the value. So on dividing, we get T equal to, here our concern is T3. So T3 will be equal to 28 degrees centigrade, right? So this is solution, and we will do one more question that is given at the end of the text. But before that, let's see other related concepts. So there is law called Stefan-Boltzmann law. So its statement is total energy radiated by perfectly black body per unit area per second. So here if we denote that this is E denotes energy per unit area per unit time, right? So according to this law, total energy radiated per unit area per unit time E is proportional to fourth power of absolute temperature of the body surface. So if body surface has temperature T, then this energy divided by energy per unit area per unit time is proportional to E proportional to T power 4, where T is absolute temperature of the surface of the body, right? Here we can use a constant E equal to sigma times T power 4. This sigma is called Stefan's constant, right? Its value is 5.67 into 10 to the power minus 8 joule second minus 1 meter minus 2 Kelvin minus 4, right? So this value you don't have to memorize, because while doing numerical questions it will be provided in the table. So just you should know that this is law only. Now if H is a rate of radiant energy, so radiant energy how to find? So H is rate of radiant energy. Radiant energy means energy in previous formula. So here energy times area is radiant energy. So we can write H equal to E times A, and in previous formula we have written sigma T power 4 as E. So this will become sigma A T power 4. Up to here I think there is no problem. Now, sorry. If this black body is enclosed in a enclosure of temperature T0, then there will be change in formula, and in that case E will take the form if enclosure has temperature T0, then E will change. Initially it was sigma T power 4. Here we have to write sigma T power 4 minus T0 power. Correct? Now, if this is not a perfectly black body, in that case emissivity will also be multiplied. If body is not perfectly black body means it absorbs all the radiation falling on it. Perfectly black, in that case we include emissivity. So in that case new formula will be epsilon times sigma T power 4. In case of enclosure this formula will be used. Here without enclosure and with enclosure, here it will be sigma times epsilon times T power 4 minus T0 power 4. So this is Stefan's Boltzmann law, and now there is Wien's displacement law. So Wien's displacement law is simple. It relates wavelength and temperature of the surface, that is lambda m proportional to T, where T is absolute temperature and this is lambda is wavelength of radiations emitted. That's obvious. So we put a constant lambda m, and we put constant as b. That is called B's constant proportional to b into, sorry, so proportionality constant if we want to write. So here I think law I stated wrongly, because this wavelength is inversely proportional to temperature. So lambda m proportional to 1 upon T, lambda m into T equal to a constant, say B. So here B is Wien's constant, right, whose value is fixed, and this is equal to B has value 2.9 into 10 to the power minus 3 meter per Kelvin. Any problem? Why B has this unit? So not per Kelvin. Here lambda is measured in meter because it is wavelength. Temperature is measured in Kelvin. So it is meter Kelvin, right? So you have understood the Wien's law, and it's a practical application if you understand. So suppose there are two bodies. One body has, say, suppose this is one body. Its temperature is, say, T1, and there is another body. Its temperature is T2, and T1 is, say, greater than T2. And suppose its wavelength emitted is lambda 1 and its wavelength emitted is lambda 2. So if T1 is greater than T2, then lambda 1 will be less than lambda 2, isn't it? And this explains the greenhouse effect. What is that? Means the radiations emitted from the sun has, since sun has higher temperature, suppose temperature T1, and this is earth, right? So here wavelength is, say, lambda 1, which will be very small. When these radiations enter the earth's atmosphere and it touch the atmosphere, it touches the earth's surface, and the earth's surface temperature of earth is, say, T2. In that case, if we apply this concept, lambda 1 T1 equal to lambda 2 T2, and as I told you that T1 is greater than T2, temperature of earth will be very less as compared to the temperature of sun. So obviously wavelength lambda 2 will be very large as compared to lambda 1, right? So size of radiations will be larger, hence they will be trapped by the earth's atmosphere, correct? So I think you have understood. In this video, this is all. We will study numericals in next video. Thank you for watching. Team Educate